All right, thanks so much. So cluster algebras. So first of all, they're introduced by Fomin Zeleninsky. In 2002. And also now, so this is a paper. There's also now a textbook. Fomin, Williams, Zeleninsky. They're kind of putting the chapters on the archive as they go. So this is like an ongoing textbook. So it's very nice, read that. Maybe don't read this now. Cluster algebras, it's a little bit, it's a great subject. I love cluster algebras, I work on them, but the definition is not very nice. It kind of sucks. So I'm going to try to explain it today, but it takes a while. And if you see this for the first time, it's probably not going to be very beautiful to you, but please keep in mind that it's actually, maybe the cluster algebras are beautiful because they show up in many places. It's like one umbrella which unifies a lot of math. And so, like if you look at the textbook, first of all, there's a lot of math, and then there's the definition. Right? There's like chapter 3 is where the definition actually is. And so I'm not going to have time to review lots of math, so I'm just going to try to quickly give a definition and maybe give one cool example. All right, so definition 1, a quiver Q is a directed graph without directed cycles of length 1 and 2. So these two things are forbidden, edges to itself, or pairs of opposite arrows. Everything else is fine. And I can have multiple edges. Yeah, I can have triangles. So it's just only these two things are not allowed. And so here's another. I'm gonna give a couple definitions, then maybe give an example. So an ice quiver is a quiver together with so basically we declare some vertices to be mutable and the rest to be frozen. With vertices partitioned into mutable and frozen. So example, here is a random quiver. Maybe 1 is frozen, 2 is frozen, 3 is mutable, 4 and 5 are also mutable, and maybe some arrows. I don't know. So double arrow here. Something like this. So the boxed vertices are frozen. And so that's basically, for any quiver, you get the cluster algebra. For any ice quiver, you get a cluster algebra. And so the main kind of combinatorial operation that you can do on quivers is quiver mutation. So given a mutable vertex of Q, mutable, you can define another quiver. Mu sub j of Q is obtained from Q by the following algorithm. So step 1 is the trickiest step, is you create shortcuts. So for each pair of an incoming arrow and an outgoing arrow, so for every 2 path like this, I'm going to create a shortcut. So I'm going to create a new arrow from I to k. Which maybe, yeah, let me try to do this. So let me copy this quiver and try to do this procedure step by step. So maybe use another color. So I'm supposed to look for all 2 paths which pass, let's say this is mutation at vertex 3. So there's like a 2 path that goes from 2 to 3 to 5. So I'm supposed to create another arrow from 2 to 5. And also from 2 to 3 to 1. So I'm supposed to create an arrow from 2 to 1. And there's 2, so there's 2 incoming arrows from 4. So I'm going to create 2 shortcuts from 4 to 5 and 2 shortcuts from 4 to 1. So that's step 1 for me. And step 2 is I'm going to reverse all arrows incident to my vertex j, right? So this is easy. So there's 5 arrows here. I'm just going to reverse all of them. All right. And so the last part is, as you can see, this is not quite a quiver. Why is it not a quiver, by the way? Because I have these arrows. So yeah, between some vertices, I'm going to maybe have like 5 arrows this way and 3 arrows the other way. So I'm just going to cancel them out. Like I'm going to subtract one from the other. So cancel out all pairs of opposite arrows. In this case, I'm gonna erase these 2 arrows, and out of these 3, so there's 2 in one direction and 1 in the opposite direction. So I'm gonna cancel out 1 pair, and I'm gonna be left with this. Yeah, and so one technical comment is that arrows between frozen vertices are always kind of automatically omitted. So whenever you see an arrow between 2 frozen vertices, you just kind of erase. You go like this, and so they don't really matter. You can always just erase all frozen arrows that you see. All right. So yeah, if you see this for the first time, this is some kind of weird combinatorial operation that you can do. And any questions, by the way, on the definition? Yeah, so it's a combinatorial operation, and already here there are some open problems and some kind of, if you understood the talk up to here, then you're already kind of done, because a lot of the depth of the theory is going to be visible to you just from looking at the quivers. But also, it turns out that many combinatorial operations can be kind of reformulated in the language of quiver mutations.
So if you keep mutating at the same vertex, does it sort of stabilize?
Oh, nice. Yeah, great question. So what happens if I mutate at the same vertex again? I'm going to go back. Yeah, it's actually a very non-obvious fact from this. Yeah, so it's maybe exercise. Is that mutation is an involution. Mu j of mu j of Q is Q. Yeah. So if you like, you can try to mutate this one again, and hopefully you're going to get back here. All right. So, any other questions, by the way? All right. So, yeah. Quiver mutation can emulate a lot of nice combinatorial things that we all like. So, the Ranian example for today's talk, we did some kind of reading class with students on cluster algebras, and I asked them, like, what's the coolest thing I should present? And they said triangulation. Well, some of them said triangulations. So what I'm going to do is talk about triangulations. And so let's say P is a polygon. It's an n-gon, like this. And then let's say T is a triangulation. Of P. So just subdivide your polygon by diagonals into triangles with no vertices inside in the interior of the polygon. So to this data, I'm going to associate a quiver. Q sub T using the following procedure. So the frozen vertices of the quiver correspond to the sides of the polygon. Maybe I should draw. So these are going to be my frozen vertices. And the mutable vertices of the quiver are going to be the diagonals of my triangulation. So in this case, there's 3 mutable vertices. And the arrows of the quiver are going to be given as follows. For every triangle of T, there is going to be kind of 3 vertices at the sides, like at the midpoints. And so you introduce 3 arrows which go clockwise. So there's 3 arrows. Maybe here I mean the arrows between the frozen vertices. So this is this red thing. Sorry. This is the quiver Q sub T. And so far, you can associate a directed graph to many objects. But what's nice is that what does quiver mutation correspond to in terms of triangulations? Maybe somebody can guess, or somebody who doesn't know the answer. Flip. Did you say flip or did you say something else? Oh, yeah, okay. Flips. So claim is that flips. So first of all, what is a flip of a triangulation? In a triangulation, you can choose any diagonal. If you choose any diagonal, it belongs to a quadrilateral. Right? It belongs to 2 triangles which form a quadrilateral. So a flip is you pick a quadrilateral and then you replace the diagonal with the only other choice. And so the claim is that flips. So if T1 and T2 are related by a flip. And then the corresponding two quivers are related by a single mutation. To draw a picture, right, there's going to be 5 vertices. And the one in the middle is going to be mutable, right, because it has to be a diagonal, because there's triangles on both sides. And if I mutate, I get this. And now if you look at the definition, right, so all the arrows incident to this vertex got reversed. And also all the arrows, the 4 arrows on the outside got kind of, I took the complement of those arrows. So yeah, you can kind of see that this works. Does it make sense to people, or should they? Okay. Yeah. So yeah, at least combinatorially, this is one nice example of cluster mutation. And people can't see this part, right? Let me erase. Yeah, maybe I should say one more thing. So here, one cool thing about triangulations is that, so in the quiver, you can mutate any mutable vertex. Right? In the triangulation, you can flip any diagonal. And also, any two triangulations, two triangulations of the same polygon are related by flips. So the conclusion is that if you start with one of those quivers and you mutate in any possible way, you get finitely many quivers, right? Because they're all going to correspond to triangulations of which there's Catalan many. And okay. So now let me try to explain. So this is kind of the combinatorial level. This is the first level, underlying cluster algebras. And the next level is seeds. Seeds, or cluster variables, is basically, so let's say, let me fix some field. Let F be a field. So let me be the ambient field. So it doesn't really matter what it is, but usually F is just the field of rational functions with complex or real coefficients in x1, x2, in some set of variables. Something like this. And then, so a seed is just a pair, so it's a pair Q comma F, where F is just an assignment of elements of the field to the vertices of Q. F sub j, j is a vertex of Q. F sub j belongs to the field. And so now let me define seed mutation. Q is a quiver.
What is it?
Q is a quiver. So it's a quiver with some extra data. So, and then you can mutate not only quivers, but also seeds. So seed mutation. If you have a seed q comma f, and j is a mutable vertex of q, then you can mutate mu sub j of the seed q comma f is going to be a new seed q prime comma f prime, where q prime is the mutation of q, and f prime is given as follows. You basically, it only changes the jth value of f. So f prime I is equal to fi for I not equal to j, and f prime sub j, so that's where the interesting formula comes in. It's the product over all incoming arrows, f sub I, plus the product over all outgoing arrows, j to k, f sub k, divided by f sub j. Yeah, I can't write f sub j. Maybe let me put it here. Okay. So you take, and this is a product over arrows. So there's many arrows, incoming arrows, then you take fi to the corresponding power. All right. So maybe let me continue this example. So f sub 3 prime is going to be what in this case? Yeah, let somebody can tell me. Yeah, so let's say for this quiver, yeah, so let's say this is f1, f2, f3, f4, f5, and this is still going to be f1, f2, f4, f5, but this guy's going to change.
So
but in this product, the arrows are read in the initial quiver Q or in the new quiver Q prime?
Yeah, it doesn't. So the question is whether these arrows, I should look at the original quiver or the mutated one, and the answer doesn't matter because I'm only looking at arrows that are incident to J, and those are just reversed. Okay, so if you reverse, the sum stays the same. F3 prime is
f2 times f4 squared, right? Plus f1, f5.
F5.
Everything divided by f3 from this.
Yeah, thank you. So that's a formula. Doesn't look very pretty again, but it is. So that's this is almost the definition of a cluster algebra. Yeah, so you can start with a seed and then you can mutate. Maybe I should leave this blackboard and not erase this part. Okay, so what about triangulations then? What happens if let's say I choose a triangulation. Maybe, just look at a quadrilateral. So let's say I apply a flip. So there's maybe f1, f2, f3, f4, f5. Then my quiver is gonna look like this. So f5 prime times f5 is f2, f4 plus f1, f3. Does this look familiar to anybody? Ptolemy relation for cyclic quadrilateral. Nice, thank you, Sanjay. Yeah, indeed, so here's a reminder. Yeah, I don't know, I don't think they do this in high school, but it's year 100, so it's Ptolemy's theorem. If P ABCD is an inscribed quadrilateral or a cyclic quadrilateral, then the product of the diagonals, so the length of the diagonals, AC times BD, is the sum of the products of opposite sides. AB times CZ plus AD times BC. So yeah, somehow, in the case of triangulations, this formula recovers Ptolemy's theorem, right? If you imagine that your entire polygon was, so if I don't know if I should write this down. So let's say I draw a bigger, maybe an inscribed hexagon, and I choose some diagonals. And then, if I specialize my cluster variables to be the length of all these diagonals, so x1, x2, x3, x4, x5, x6, x7, x8, x9, and then I can apply any flips, and then the length of the diagonals are going to change precisely according to the cluster mutation. All right, any questions on this, or is it? Yeah. So there's one requirement I haven't told you, which is these elements should be not just any elements of the field, they should be algebraically independent. They're required to be algebraically independent. Okay. So it's just how the theory works. Otherwise, some things break down. And so yeah, we just usually assume, yeah.
Sorry, what if you have a non-inscribed polygon? Then it's not a cluster algebra, right?
Yeah. So far, I haven't defined the cluster algebra. But if you have a non-inscribed polygon, then these lengths are not going to satisfy the cluster relation.
Or any other structure,
Yeah, but there's things you can do. You can take like a hyperbolic surface and measure geodesic lengths, and then it's going to satisfy. Yeah, so there is a way to make these kind of algebraically independent by looking at Teichmüller theory. So yeah, but yeah, in the plane, once you know the size, length of an inscribed polygon, then you know all the diagonals. So yeah, Nicholas.
But you can also replace the lengths by complex vectors. Then Ptolemy is true again. So then you get sort of a complex valued.
But it has to be inscribed.
No, then it doesn't have to be inscribed.
Yeah, so let me explain that part. So yeah, there's a way to fix the fact that these are not algebraically independent. So let me try to attempt to fix this. So fix, let's say M is a 2 by n matrix. 2 by n matrix with, let's say, complex or real entries. And let me look at the columns. So M1, M2, etc., M sub n, so I have n columns. And let me say the delta, so if for two indices A and B, A less than B, let me say delta AB is the determinant of M, A, M, B. So just a 2 by 2 determinant of my matrix. So then there's something called the Plucker relation. Just a relation on determinants of a matrix which reads delta AC, so for any A less than B, less than C, less than D, between 1 and n, delta AC, delta BD is equal to delta AB, delta CD, plus delta AD, delta BC. So in some sense, it's actually a generalization of the Ptolemy relation. But it's sort of more general. So let me try to give an example. Where do I give an example? Maybe here. Oh, can I do? No, it doesn't work. Yeah, anyways. Maybe if I pick some random matrix. P, 0, 0, 1, X, Y, minus Z, W. Totally random matrix. Then you can measure all of these determinants. So delta 1, 2 is PY, delta 1, 3 is P, delta 1, 4 is PW, delta 2, 3 is X, delta 2, 4 is XW plus YZ, and delta 3, 4 is Z. And yeah, I'm just checking that this works. So if you compute delta, delta 1, 2 times delta 3, 4 plus delta 1, 4 times delta 2, 3, this is what delta, it's PY times Z plus delta 1, 4 PW times delta 2, 3 is PWX, and so presumably this equals to delta 1, 3, delta 2, 4. That works? Nice. And so the other thing that you can see, which hopefully works out, is that if you take this quadrilateral, you pick a triangulation. A, B, 1, 2, 3, 4. Right, so I have these 5 variables, right? I have these 5, let's say I label every edge by a minor, by the corresponding minor of the matrix. So delta 1, 2 is PY. Basically, I use all deltas except for 2, 4. So I use this one, this one, this one, this one, and this one. And you can see that these are algebraically independent. Unlike in the case of inscribed quadrilaterals, here I actually have an honest seed. Right, so delta 2, 4 is expressed in terms of the other ones, right? According to the mutation, right? You can express delta 2, 4 in terms of the rest using cluster mutation. Right? And you would get another cluster corresponding to this triangulation. So any questions so far? No questions? All right. So, I mean, some questions that you may have is, first of all, I took 2 by n matrices. Is it special to 2 by n, or does it? Can we generalize to matrices k by n? And the answer is yes. Hopefully, I have time to tell you, but if not, then it's just a cliffhanger. So another question is, what does this all have to do with the dimer model? With the dimer model. You know, it's a conference about dimers. For some reason, they ask some guy to give a tutorial on cluster algebras. Why? How is that related one to another? And yeah, hopefully I talk about that as well. And also, you know, what is a cluster algebra? As you can see, I'm masterfully avoiding giving you that definition. So I'm gonna start with the part 3. So because otherwise people will get upset that I didn't define. So yeah, part 3, cluster algebras. And as I said, we are basically almost there. So let's say for simplicity, I label my vertices of the quiver. So let's say let Q have vertices, let's say mutable vertices, 1, 2, all the way up to n, and frozen vertices, n plus 1, etc., n plus m. And yeah, so then I take my field, just ambient field, to be the field of rational functions with x1 in x1, x2, etc., up to x n plus m. And so let's say I pick an initial seed, q comma x be an initial seed. So it's a seed, right? X is just an assignment of basically just independent variables to all the vertices of my quiver. I start with that, and then I mutate. I mutate in all possible directions. So write down all seeds obtained from q comma x, right, from my initial seed by applying a sequence of mutations. And so I'd like to emphasize that I really do this in all directions. So in general, usually I get infinitely many seeds, right? Because, you know, if you start with an arbitrary quiver, you apply these mutations. What usually happens is that the number of arrows grows kind of exponentially, right? There is this part where, like, for every 2 path, I create a shortcut. So if there is like A arrows here and B arrows here, then I'm going to get A times B arrows here. So usually this grows pretty quickly. Yeah, well, at a single vertex, it's an evolution.
You mean to say, so by saying in all directions, you mean to say that you keep applying mutations?
Right, yeah, so I start with my initial quiver, and then I apply mu I1, I get some other quiver, then I apply some other seed, mu I2, etc. Mu IN, I get another quiver. And I do this for all possible sequences of vertices, yes. So yeah, I get some kind of completely intractable collection of quivers with like rational functions on the vertices. Every one of these is going to be, so elements, so all elements of my ambient field obtained this way are called cluster variables. Yeah, so I'm going to give some terminology, and then I'm going to give an example. And yeah, so like, and so along the way, I encounter many different cluster variables. And so, but cluster variables in a given seed are set to form a cluster. Cluster variables in a single seed form a cluster. So that's a definition of the word cluster. Okay. And finally, cluster algebra.
So this assumption of algebraic independence means that basically defines that they're all different for different.
Well, they need not be all different. So it could happen that you mutate, and then you end up back at the same seed.
And so in that case, you still view them as a different cluster or the same cluster?
Well, the same cluster, yeah. So, I mean, yeah. If two seeds are the same, then they are kind of identified. But for the purposes of this definition, it doesn't matter. You just mutate in all possible ways, write down all of the cluster variables, and yeah. So, and then you define the cluster algebra, which so definition. Cluster algebra A of Q is, first of all, it's a subalgebra of the field. The subalgebra of the field of rational functions is the C subalgebra generated by all cluster variables. Yeah.
First of all, if you do the sequence of mutations and you happen to get the same quiver as before, is the seed gonna be the same?
If you get the same quiver, the seed is not in general going to be the same. Yeah. It's example. If you take x1, double arrow x2, and you mutate, I mean, no matter how much you mutate, you get the same quiver. Even with a single arrow, you get the same quiver. But with double arrow, the functions are going to grow, not exponentially, but I mean, yeah. The functions are going to grow, but the quivers is going to stay the same, basically.
The functions are going to be some power x1 to some power over x2.
No, actually, let me, that's an intriguing example. Let me just plug in x1, x2 to be 1. Okay, we can always plug in some values and then mutate. Right, so you start with 1, 1, and then you mutate, let's say, here. So you get 1 squared plus 1 over 1, right? And the formula, if you mutate, is x2 squared plus 1 over x1, according to the definition. So 1 squared plus 1 over 1, that's a 2. Yeah, just write 2. And then I mutate here, so I get 4 plus 1 over 1, that's 5. And then I mutate here, I get 25 plus 1 over 2. That's 13. I guess, so yeah, some people are not going to see what's going to happen behind this line, but let me continue here. So 169 plus 1 over 5 is what? 34. Nice. What's 34? What? Five, 13, 34. Fibonacci, yeah. Not every Fibonacci number, but you skip 8 and 21, but you skip every second Fibonacci number. So yeah, Greta, that's the, it's, I guess, grows exponentially.
So that you have a +1, right?
Yeah. Without the +1, it would be kind of trivial. But it's very, the fact that you get Fibonacci numbers, first of all, the fact that you get integers. I mean, Terence is going to talk about that, but at some point I divided by 5. At some later point, I'm going to divide by 13. It's actually quite impressive. So yeah, anyways, but yeah, back to the definition. So that's the definition of a cluster algebra. And I guess maybe I should try some actual examples.
Can I ask one more question?
Sure.
So can you actually get all these functions in the algebra as by a sequence of mutations?
So does the cluster algebra equal the entire field, you're asking?
Well, all the ones that are, does the cluster algebra equal the AQ? Because you're saying it's generated by the variable.
Well, what do you mean? I mean, by definition, it's the subalgebra generated by whole cluster variables.
I guess the question is whether the product of two elements that you get as
it's not
clusters.
obvious then that it's
Well, a product of two cluster variables in general is not a cluster variable, but it belongs to a cluster algebra because in algebra you're allowed to multiply. Yeah.
Okay,
You can multiply two things. You can also multiply them by a number. Yeah, and add them up. So you get a whole bunch of elements here, and it's completely unclear what this is.
Is there a nice notion of dimension of growth of dimension of this? Or is it always just trivially more or less the size of the number of variables to be?
You mean after like n mutations, how many? Yeah, usually it's unpredictable. So if you start with a quiver, I mean, I can tell you when it's going to be finite. It's going to be finite if and only if Q is a Dynkin diagram. It's an orientation of a Dynkin diagram or something that's mutation equivalent to that. So if I show you, a quiver like this.
Which Dynkin diagram? Not every Dynkin diagram, right?
Well, I mean, ADE Dynkin diagrams, yeah. Finite type Dynkin diagrams, yeah. So if I show you a quiver like this, right, you can't really tell if it's going to be infinite or finite. But if you mutate at this vertex, there's going to be a shortcut, so this arrow is going to cancel out, right? So if I mutate at 2, I'm going to get a path. And so I see that this is type A, and so this is going to be finite type. But in general, it's a tricky problem to recognize. You start with E8 quiver, you mutate some number of times, you get some crazy looking quiver. So yeah, there's a deep theorem by Fomin-Zelinsky that when you get finite type. And
there's no intermediate regime like there's somehow the sub-exponential ones.
There is intermediate, yeah. So if you take an affine Dynkin diagram, yeah. So there is, like for example here, this is actually, this is a 2-cycle. It's a affine type A example. And so in general, these numbers would grow not exponentially, but quadratic exponent. Like it's e to the n, I think something like this, they would grow. But here they just grow like e to the n. There's also a regime where it's e to the n squared. So there is like intermediate, yeah, and it's not just Dynkin diagrams, you can take products of Dynkin, yeah, anyways, there is a complicated story there. Any other questions? Okay. Let me just still try to do just one example, or maybe several small examples. Example let's say I take a quiver just on two vertices, one of which is frozen, so a single arrow. And my initial seed is, I label them by x1 and x2. x2 is frozen. Okay, and so now I'm supposed to apply all possible mutations. So, I mean, I have this seed. I also have, I can mutate at the first vertex. I'm not allowed to mutate at frozen vertices. So I mutate vertex 1, and I get x2 plus 1 over x1. Okay, and I can mutate once more and get back to the initial seed. So that's all I get. That is my, so my cluster variables. There's going to be 3 cluster variables: x1, x2, and x2 plus 1 over x1. And there's going to be 2 clusters. Right, x1, comma x2, and x2 plus 1 over x1, comma x1. And, well, sorry, x2, yes, thank you. And, I mean, so you have some kind of, maybe it's not that interesting. So the cluster algebra, I can't even really say anything about it, right? Because, so you take these functions, right? You take the 3 cluster variables, and then you can multiply them in all possible ways, take all sums, linear combinations. You get some kind of set of rational functions. One thing I can say is that it's isomorphic, right? If you replace this guy by x1 prime, just declare it as a free variable, then it's isomorphic to the polynomial ring. I mean, by definition, it's the polynomial ring in these 3 variables modulo a relation that x1 times x1 prime is x2 plus 1. Right? I have the mutation relation, and so my 3 variables with like 1 relation between them. And so you can think of this as, you know, there is, if you take x times y equals z plus 1, and you draw it in the 3-dimensional space, you get the hyperbolic paraboloid, or whatever the name is. So you can think of this algebra as a, you know, as the ring of polynomial functions on the hyperbolic paraboloid. I was looking at Wikipedia yesterday, and I found out that Pringles are actually, like, the shape is actually hyperbolic paraboloid, like on the nose, not just some random kind of saddle. So yeah, it's, I mean, this is what happens more generally. More generally, the cluster algebras, I mean, you can think of them as some kind of commutative rings and ask, are they interesting as commutative rings? And a lot of times, we can prove theorems that even though the definition is completely intractable, the ring itself is the ring of polynomial functions on some kind of interesting algebraic variety. So that's the kind of stuff that you recover. In general, it's hard to write down these relations because, you know, there's infinitely many mutations you apply, so it's even unclear when it's finitely generated or not. But there's always, you know, if you like algebraic geometry, you can always associate a scheme to a commutative ring, and a lot of times it's an interesting scheme. All right, so let me maybe, I mean, another thing you can look at is maybe triangulations, right? It's an exercise. Just write down all clusters and cluster variables, or find the number of clusters, number of cluster variables for the cluster algebra A of Q sub T, where T is a triangulation of an n-gon. So, and think about what's the variety, like what is the cluster algebra? What's the interesting variety that the cluster algebra encodes? I can tell you that. So A of Q sub T is basically the ring of polynomial functions on the Grassmannian. On the Grassmannian of two planes inside the n-dimensional space. So it's very closely related to matrices, two-n matrices, but you just take the row span of the matrix, not because I'm only looking at maximal minors, not any minors. So yeah, let me say one cool fact. So cluster algebras are very general, but still there are some theorems that people prove that are true for all cluster algebras. And so here's one theorem, which I guess Terence is going to also explain this in more detail, but let me still mention it. It's kind of cool. So for any cluster algebra, let's say for any quiver, any cluster variable is a Laurent polynomial in the initial cluster variables with positive integer coefficients.
True for any cluster, right?
For any cluster algebra, any cluster in any cluster algebra.
Any cluster in any other cluster. It doesn't have to be initial, right?
Yeah, you start with the initial cluster, you mutate a bunch of times.
Mutate it back. The initial cluster is a Laurent polynomial in any cluster.
Yeah, initial cluster is Laurent polynomial in any other cluster. But yeah, so I don't know, is this theorem surprising or is it trivial? What do people?
The integer part is surprising, right? The fact that it's a Laurent polynomial is trivial.
This is trivial. Okay. And this is surprising, or is this surprising? Yeah. So actually, yeah. This is none of these is integer maybe is trivial, but these two are super hard. Well, I mean, this one's much harder than this one, but this one is not what you. So let me give one example. I mean, first of all, what is a Laurent polynomial? Is a rational function which has some plus signs in the numerator, but it only has a monomial, a single monomial in the denominator. Okay, but when I mutate, like if I start with the initial cluster and mutate once, yeah, I have a monomial in the denominator.
Maybe I was going with a different definition of Laurent.
Yeah, right. Yeah. But I mean, I'm not blaming you, but it's usually what people say. Usually, the first reaction, including like my first reaction, is that this is trivial because you mutate once, it's divide by xi, but it's not trivial because you keep at some point you're going to have to divide by this, and it's going to cancel out. That's the. Let me give you one example. And yeah, the positivity was like conjectured and then open for 20 years and then recently proved by Gross-Hack and Kilkon-Savage. So it's like, yeah, this is non-trivial result, which is true for all clusters. Yeah, let me try one example to illustrate this point. Actually, so the Laurent polynomial phenomenon is even here, right? I mentioned that I have to divide by 13. 13 is when I set x1 and x2 to be 1. Right? In general, it's a polynomial with 13 terms, and you have to divide by it, and it's going to cancel out. So this is, yeah. So it's completely non-trivial, and yeah, maybe. So this is in the original Fomin-Zelensky paper. This is Gross, Hacking, Keel, Kontsevich. Yeah. So let me try one example, which is. Maybe just call them x and y. So let's say I have two non-frozen, just two mutable variables and one arrow. Okay? And then I'm going to start mutating. So I mutated x, I get y plus 1 over x. And then mutated y, I get, well, let's see, y plus 1 over x plus 1 over y. This is y plus x plus 1, y plus x plus 1 over y. And now I'm in trouble, right? Because, okay, so I mutate here, and what do I, like, is it going to cancel out, or like, is the theorem even true? So you can, let's mutate. So I take this guy plus 1 divided by y plus 1 over x. And so this becomes, oh, did I forget? Okay, this is xy. Okay, I did get in trouble. So xy. So I get xy plus x plus y plus 1. The x cancels out, so I get y is y plus 1. And so you can see that the y, somehow you cannot see this part. The y plus 1 is going to cancel out from the numerator. And what I'm going to end up with is x plus 1 over y. And now I mutate here. So this thing plus 1 divided by this, you can probably see this. Yeah, if you take this guy plus 1 divided by this, you get just x plus 1 over y plus 1 divided by x plus y plus 1 over xy. This is equal to x. So the next seed is going to be x plus 1 over y, and the next one is going to be x plus 1 divided by this, which is y. So I do get back to my initial seed, kind of reflected. Yeah, there is another cool property, which is related to Dima asked about, what Dima asked about, which is surprising periodicity. And yeah, I mean, it has to do with the fact that this is a type A Dynkin diagram, but you can make this work even for non-Dynkin diagrams somehow if you mutate in a particular way. So, any questions on this? Yeah.
You know more clusters where this periodicity stuff happens?
Yes. Yeah, I have a paper that classifies all of them, and the answer is there are some giant. Yeah, you can take two copies of E8 and you can mesh them together in some kind of crazy. Yeah, there is a classification. They are in bijection with commuting Cartan matrices. That's the easy answer. So yeah, go ahead.
Quivers are finite always or not?
No, the quivers are not finite. But if you mutate in a particular alternating, like if your quiver is bipartite and you mutate at black and white, so then yeah, we know all the cases where this holds.
Okay.
When you say you direct a Dynkin diagram, is there a specific direction or any
orientation of it? Yeah, all orientations of a tree are related to each other by mutations. So they're all kind of in the same mutation class. Okay. Yeah, so I was going to talk about dimers. Maybe, yeah, let me just stop because Terence is going to talk about dimers. And is that, yeah. So, yeah, maybe we should just stop here. All right, so thanks a lot.